Hello there and welcome to Sleep Science Chronicles. Tonight, we drift into one of the universe's most patient and beautiful processes, the birth of planets. We will follow the quiet journey from drifting specks of dust to whole worlds, rocky spheres with iron hearts, gas giants wrapped in swirling storms, ice worlds where diamonds may fall like rain. This is a story that unfolds over millions of years, in the cold darkness between stars, in spinning disks of gas and dust, in collisions so slow they look like embraces. It is a story written in gravity and patience, in the gentle pull of matter toward matter, in the way tiny grains of dust can become mountains, oceans, skies. Some of what we will discover tonight is ancient, processes that shaped our own Earth billions of years ago, long before any eye existed to witness them. Others are happening right now, around young stars scattered across the galaxy, in nurseries of dust and light, where new worlds are slowly taking form. You do not need to remember every detail. Let these facts drift past you like clouds, like motes of dust catching distant starlight. Some may linger. Others may carry you gently toward sleep. Either way, you are welcome here. Wherever you are resting tonight, let your breath slow. Let the weight of the day begin to ease. We are going to travel very far and very long ago to the places where worlds begin. And just before we begin, if these calm and curious explorations help you unwind or spark a quiet sense of wonder, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. But for now, let your shoulders soften. Let's begin. Long before there were planets, there was dust. Not the kind that gathers on shelves or drifts through sunlit rooms, but something far older and stranger. Cosmic dust, scattered across the vast emptiness between stars. This dust is the raw material of worlds. Every planet that has ever existed, including the one you are resting on tonight, began as nothing more than microscopic grains floating in the dark. Cosmic dust is unimaginably small. A single grain might measure only a fraction of a micrometer across, smaller than the wavelength of visible light, smaller than bacteria, smaller than almost anything you could picture. If you gathered 1,000,000 of these grains together, they might form a speck barely visible to the human eye. And yet, from such tiny beginnings, entire worlds are born. This dust is not simple. Each grain carries its own history, forged in the heart of a dying star or blown outward in stellar winds, or created in the shock waves of ancient explosions. Some grains are made of silicates, the same family of minerals that form rocks and sand on Earth. Others are carbon-rich, dark as soot. Still others are coated in delicate films of ice, water, ammonia, methanes frozen in the deep cold of space. The origin of cosmic dust lies in the death of stars. When a star exhausts its fuel and begins to fade, it often sheds its outer layers into space. Red giant stars puff out shells of gas and dust over thousands of years. More massive stars explode as supernovae, scattering freshly forged elements across light years. The dust that drifts through the galaxy today is the ash of countless stellar generations, recycled over billions of years. Some of this dust is older than our solar system. Scientists have found presolar grains embedded in meteorites, tiny crystals that formed around distant stars before our sun was born. These grains survived the formation of our solar system, carried within asteroids and comets like messages from an earlier time. Holding a meteorite that contains presolar grains is holding something older than the Earth, older than the Sun, older than anything else you could touch. Dust drifts through the galaxy in vast clouds, sometimes stretching across dozens of light years. These clouds are cold and dark, blocking the light of stars behind them. From Earth, they appear as dark patches against the glowing backdrop of the Milky Way. Not empty voids, but regions so thick with dust that light cannot pass through. Inside these clouds, temperatures can drop to just a few degrees above absolute zero, cold enough to freeze almost any molecule. Despite its seeming fragility, cosmic dust survives remarkably well in space. The vacuum protects grains from erosion. The cold preserves delicate structures. A single grain of dust might drift for millions of years, slowly tumbling through the dark, waiting for gravity to gather it into something larger. Dust is patient. Dust has time. The composition of dust varies depending on where it formed. Dust born in the outer envelopes of carbon-rich stars tends to be dark and sooty. Dust from oxygen-rich stars often contains silicates and oxides. The interstellar medium blends these sources together, creating a mixture that includes metals, organics, and ice in proportions that shift from cloud to cloud. This variety means that no two regions of dust are quite identical. When starlight passes through a dust cloud, something beautiful happens. Shorter wavelengths, blue and violet light, scatter more easily than longer wavelengths. The dust acts like a filter, reddening the light of distant stars and softening their glow. This is why some nebulae appear tinged with warm colors, their light gently scattered by the dust that fills them. The same dust that blocks light also paints it. In the densest parts of dust clouds, molecules begin to form. Atoms of hydrogen, oxygen, carbon, and nitrogen collide and bond in the cold darkness. Water ice coats the surfaces of grains. Complex organic molecules, the building blocks of chemistry, assemble in the shadows. These molecular clouds are not just reservoirs of dust and gas. They are laboratories where the ingredients of planets and life slowly come together. And so the dust waits. It drifts. It gathers. Across millions of years, gravity begins to stir. The story of planets begins not with fire or collision, but with the quietest of forces. The gentle pull of matter toward matter, grain by grain, in the patient darkness of space. A dust cloud can drift unchanged for millions of years. The grains float in equilibrium, their random motions balanced against the faint pull of their collective gravity. But this balance is fragile. Sooner or later, something disturbs it. A ripple passes through the cloud, and the long process of collapse begins. The trigger might be a shock wave from a nearby supernova, the violent death of a massive star sending a pulse of energy racing through the interstellar medium. When this wave encounters a dust cloud, it compresses the gas and dust, pushing regions that were nearly uniform into denser clumps. These clumps now have enough mass concentrated in a small enough space for gravity to take over. Other triggers are gentler. The slow rotation of the galaxy creates spiral density waves, regions where stars and gas naturally crowd together. A dust cloud passing through one of these waves experiences compression, like traffic slowing on a highway. The increased density can be enough to tip a cloud toward collapse. Even the gentle pressure of starlight from nearby bright stars can nudge a cloud into instability. Once collapse begins, it feeds itself. As material falls inward, the center of the cloud grows denser. Greater density means stronger gravity, which pulls in material faster, which increases the density further. This runaway process transforms a diffuse cloud into a concentrated core over the course of a few 100,000 years. A blink of an eye in cosmic terms, though longer than human civilization has existed. As the cloud collapses, it begins to spin. This is not new motion, but old motion amplified. The original cloud was never perfectly still. It had some slight rotation, inherited from the turbulent flows of the galaxy. As the cloud shrinks, this rotation speeds up, the same way a spinning figure skater accelerates by pulling in their arms. The conservation of angular momentum ensures that collapse and spin go hand in hand. The spinning collapse does not form a sphere. Instead, the material flattens into a disk. Matter falling straight toward the center meets resistance from material already there, but matter falling at an angle can swing around, joining the rotating flow. Over time, the cloud transforms from an irregular blob into an elegant disk with a dense, hot center. This disk is the birthplace of planets. At the center of the collapsing cloud, temperatures rise. The gravitational energy of infalling material converts to heat, warming the core to hundreds and then thousands of degrees. Dust grains that drift too close are vaporized, their solid forms returning to gas. The center glows faintly at first, then more brightly. This is a protostar, not yet a true star, but a dense, hot mass on its way to ignition. The timescale of this initial collapse depends on the mass of the cloud. A region destined to form a sun-like star might collapse in a few 100,000 years. More massive regions collapse faster. Less massive regions take longer. But in every case, the process is slow by human standards and swift by cosmic ones. A cloud that existed unchanged for 10 million years can transform into a protostar and disk in less than 1,000,000. During collapse, the cloud fragments. Different regions within the same cloud may begin collapsing at different times or at different rates, each forming its own protostar and disk. This is why stars often form in clusters, dozens or hundreds, born from the same parent cloud, siblings separated by light years, but sharing a common origin. Our sun may have had such siblings, long since scattered across the galaxy. Not all the material in the cloud reaches the center. Much of it remains in the surrounding disk, orbiting the young protostar in a flattened structure that can extend for hundreds of astronomical units, hundreds of times the distance from Earth to the Sun. This disk contains the raw material from which planets will form. It is a reservoir of gas and dust, spinning slowly, waiting for the next stage of creation. The temperature within the disk is not uniform. Close to the protostar, the disk is hot, hundreds or even thousands of degrees. Farther out, temperatures drop steadily. At the outer edges of the disk, temperatures can fall below 50 Kelvin, cold enough for water, ammonia, and methane to freeze solid. This temperature gradient will determine what kinds of planets form where. Rocky worlds close to the star, ice and gas giants farther out. And so, from the quiet drift of dust, a new structure emerges. A protoplanetary disk, glowing faintly in infrared light, spinning around a young star that has not yet begun to shine. The dust has found a new home. The long process of building worlds is about to begin. The protoplanetary disk is one of the most beautiful structures in the cosmos. Seen from above, it would appear as a vast spiral of gas and dust, glowing in warm infrared tones, swirling slowly around a central star. Seen edge on, it would look like a dark band cutting across the star's light, a shadow made of the raw material of worlds. These disks are the cradles where planets are born. A typical protoplanetary disk extends for tens to hundreds of astronomical units from its central star. One astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So a disk might stretch from the equivalent of Mercury's orbit all the way out to where the Kuiper Belt lies in our solar system, or even farther. Within this vast expanse, countless trillions of dust grains orbit the young star, each one a potential building block for something larger. The disk is not a solid structure, but a diffuse cloud of particles and gas, thin enough that you could fly through it without noticing any resistance. If you could stand within a protoplanetary disk and look around, you might see only a faint haze. The dust is spread so thin that each cubic centimeter contains perhaps a few thousand particles, far less dense than the air you breathe. And yet this tenuous material contains enough mass to form multiple planets. Most of the disk's mass is gas, not dust. Hydrogen and helium dominate, the same elements that make up most of the universe. For every 100 grams of gas, there might be only 1 gram of dust, but that dust is crucial. The gas alone cannot easily clump together. It is too hot, too diffuse. The dust provides seeds around which larger structures can grow. Without dust, there would be no rocky planets, no moons, no asteroids. There would be only gas giants, if anything at all. The temperature gradient across the disk creates distinct zones. In the inner disk, close to the star, temperatures can exceed 1,000 Kelvin. Here, only the most refractory materials survive. Metals and silicates that can withstand intense heat. Iron, nickel, aluminum, calcium. These condense into solid grains, while more volatile materials remain as vapor. This is the region where rocky planets like Earth will eventually form. Farther from the star, the disk grows cooler. At a certain distance, temperatures drop below the freezing point of water, around 170 Kelvin at the low pressures of space. This boundary is called the frost line or snow line. Beyond it, water ice can exist as solid grains, joining the silicates and metals. The presence of ice dramatically increases the amount of solid material available for planet building. The frost line marks a fundamental divide in the architecture of planetary systems. Beyond the water frost line, other ices condense as temperatures continue to drop. Ammonia freezes at around 80 Kelvin. Methane freezes at around 30 Kelvin. Carbon monoxide and nitrogen freeze at even lower temperatures. The outer reaches of the disk become rich in these frozen volatiles. Bright grains of ice mixed with darker dust. This is the realm where ice giants and the icy bodies of the outer solar system will form. The disk does not sit still. It rotates, with inner regions orbiting faster than outer regions. Just as Mercury orbits the Sun faster than Neptune, this differential rotation creates shearing motions within the disk, stirring the material like cream swirled into coffee. Turbulence ripples through the gas, creating eddies and vortices that mix material from different regions. The disk is a dynamic environment, constantly in motion. We can observe protoplanetary disks around other stars. The Atacama Large Millimeter Array, ALMA, has captured stunning images of these disks in unprecedented detail. The disk around the young star, HL Tauri, shows concentric rings and gaps, dark lanes where material has been cleared, possibly by forming planets. The disk around PDS-70 contains 2 young planets caught in the act of being born. Glowing points of infrared light embedded in the surrounding dust. These observations reveal that disks are not smooth and featureless. They contain structure, rings, spirals, gaps, and asymmetries. Some of these features are carved by planets already forming within the disk. Others may arise from the physics of the disk itself, from magnetic fields or gravitational instabilities or variations in temperature. Each disk is unique, shaped by the particular conditions of its birth. The lifetime of a protoplanetary disk is limited. Over millions of years, the disk gradually disperses. Some material falls onto the star. Some is blown away by stellar winds or radiation. Some is incorporated into planets and smaller bodies. After 3 to 10 million years, most disks have faded away, leaving behind whatever planets managed to form. This sets a deadline for planet formation. Worlds must be built before their raw material disappears. When we look at these distant disks, we are seeing what our own solar system looked like 4.6 billion years ago. The same processes that shape those distant structures shaped the disk from which Earth was born. Every ring and gap we observe is a clue to how planets form, how our world came to be. We are watching the past unfold around other stars, learning the story of our own origins. And within these disks, invisible to even our best telescopes, the first steps of planet formation are already underway. Grains of dust are drifting closer together, beginning the long journey from specks to worlds. The first step in building a planet is almost impossibly small. 2 grains of dust, each finer than a human hair, drift close enough to touch. They stick. This tiny event, repeated countless trillions of times across millions of years, is how worlds begin. At the smallest scales, dust grains stick together through forces that seem almost magical. Van der Waals forces, the weak attraction between any 2 molecules, become significant when particles are tiny and close. Electrostatic charges built up on grain surfaces create attraction. If the grains are coated in ice, the ice can act as glue, bonding particles together on contact. These forces are feeble, but they are enough to hold microscopic grains in gentle embrace. The grains do not collide violently. In the quiet environment of the protoplanetary disk, relative velocities are low. Particles drift past each other at speeds of centimeters or meters per second, not kilometers. At these gentle speeds, collisions are more like meetings than crashes. 2 grains touch and stay together, their weak bonds unbroken by the soft impact. This is how the first aggregates form. These early aggregates are not dense spheres, but fluffy, irregular structures. Imagine a snowflake made of dust or a tangle of cobwebs. The grains stick where they touch, leaving empty spaces between them. A particle made of 1,000 grains might be mostly empty space, its solid material forming a delicate lattice. These structures are fragile, easily disrupted, yet they represent the first step towards something larger. The presence of ice dramatically improves sticking. Beyond the frost line, where temperatures are cold enough for water to freeze, ice-coated grains bond more readily than bare silicates. The ice provides a softer, stickier surface, allowing particles to adhere even at slightly higher collision speeds. This is one reason why so much solid material accumulates in the outer disk. Ice makes building easier. Laboratory experiments on Earth have simulated these collisions. Scientists drop tiny silicate spheres in vacuum chambers, watching them meet at controlled speeds. The results confirm what theory predicts. At low speeds, grains stick. At higher speeds, they bounce. At still higher speeds, they shatter. The The transition from sticking to bouncing occurs at velocities of about 1 meter per second, setting a fundamental limit on how aggregates can grow through simple collision. Growth from micrometer-sized grains to millimeter-sized particles proceeds relatively smoothly. Collisions are frequent enough and gentle enough that aggregates steadily accumulate material. Over thousands of years, a single grain might grow into a fluffy particle the size of a sand grain, containing millions of original grains loosely bound together. The disk fills with these small aggregates, drifting and colliding, slowly growing. As particles grow larger, they begin to settle toward the midplane of the disk. Small grains remain suspended in the gas, supported by turbulence like dust motes floating in air. But larger particles are less easily supported. They sink slowly toward the disk's equator, forming a thin, dense layer of solid material. This concentration of particles in the midplane increases the frequency of collisions, accelerating growth. Turbulence in the disk both helps and hinders this process. Gentle turbulence stirs particles together, increasing collision rates, but strong turbulence keeps particles suspended, preventing them from settling to the midplane. The balance between these effects determines how efficiently particles can concentrate and grow. In regions where turbulence is weak, the settling layer becomes particularly dense and particle growth proceeds rapidly. The growth of dust aggregates is not uniform across the disk. In the warm inner regions, bare silicate grains grow more slowly, hindered by bouncing and fragmentation. In the cold outer regions, icy grains stick more readily, achieving larger sizes faster. This difference will eventually manifest in the types of planets that form: smaller rocky worlds close to the star, larger ice-rich worlds farther out. By the end of this stage, the disk contains a population of aggregates ranging from micrometers to centimeters in size. The original dust has been transformed, gathered into larger structures that represent the first tangible step toward planets. But these centimeter-sized pebbles are still unimaginably small compared to a world. The next stages of growth will require new mechanisms, new processes that can bridge the gap between pebbles and mountains, between grains and worlds. And so the dust continues its patient work. In the midplane of the disk, a thin layer of pebbles orbits the young star, waiting for gravity to take over. The foundation of worlds has been laid, grain by grain, in the silence of space. Growing from pebbles to planets presents a puzzle that troubled scientists for decades. The journey from centimeter-sized grains to kilometer-sized bodies does not proceed smoothly. Something seems to block the way, a barrier that pebbles struggle to cross. Understanding how nature overcomes this obstacle reveals one of the most elegant solutions in planetary science. The problem begins with drag. As pebbles orbit the young star, they move through a thin haze of gas. This gas orbits slightly slower than the pebbles because it feels pressure support that solid particles do not. From the pebble's perspective, there's always a headwind, a gentle resistance that steals momentum with every orbit. This drag causes pebbles to spiral slowly inward, drifting toward the star. For very small grains, this inward drift is negligible. For very large bodies, gravity dominates and drag becomes unimportant. But for particles in the middle range, roughly meter-sized, the drift is catastrophic. A meter-sized boulder in the inner disk might spiral into the star in just a few hundred years, far too quickly to grow into anything larger. This is the meter-size barrier, and it seemed for a time to make planet formation impossible. The problem deepens when collisions are considered. As particles grow larger, they collide at higher speeds. The gentle sticking that worked for tiny grains no longer applies. Larger particles bounce off each other instead of merging. At still higher speeds, they shatter into fragments. The combination of inward drift and destructive collisions creates a bottleneck that simple growth cannot overcome. Nature's solution is subtle and beautiful. Instead of growing one particle at a time, pebbles find a way to collapse collectively. This mechanism, called the streaming instability, transforms the problem from one of individual growth to one of collective behavior. When conditions are right, pebbles spontaneously clump together in dense filaments that collapse under their own gravity. The streaming instability arises from the interaction between pebbles and gas. As pebbles drift inward, they drag some gas along with them. This creates regions where the gas moves faster, reducing the headwind on nearby pebbles. Those pebbles drift more slowly, allowing others to catch up. The result is a feedback loop. Pebbles concentrate into dense streams, and dense streams concentrate further. Within these streams, gravity can take over. When pebble density becomes high enough, the collective gravity of the swarm exceeds the disruptive effects of turbulence and drag. The stream collapses and thousands or millions of pebbles merge into a single body within a matter of hours or days. This body is a planetesimal, a mountain-sized object kilometers across, held together by its own gravity. The meter-sized barrier has been leaped in a single bound. Planetesimals are the true building blocks of planets. Unlike the fragile aggregates of earlier stages, planetesimals are solid bodies, dense enough to resist disruption from all but the most violent collisions. A typical planetesimal might be 1 to 100 kilometers in diameter, comparable to the larger asteroids we see today. These objects are small by planetary standards, but they represent a crucial threshold. Once planetesimals exist, gravity-driven growth becomes possible. The asteroid belt is a graveyard of planetesimals that never became a planet. Here, between Mars and Jupiter, millions of rocky bodies orbit the Sun, remnants of the early solar system that were prevented from merging into a single world. The gravitational influence of Jupiter stirred this region too violently, keeping the planetesimals apart rather than allowing them to combine. Studying asteroids today gives us a window into what the building blocks of planets looked like billions of years ago. Comets represent a different population of planetesimals, icy bodies that formed in the cold outer reaches of the solar disk. While asteroids are primarily rock and metal, comets contain abundant water ice, frozen gases, and organic compounds. These icy planetesimals were scattered outward during the early evolution of the solar system, forming the Kuiper Belt and the even more distant Oort cloud. When a comet falls inward and grows its glowing tail, we are seeing ancient building material preserved in the deep freeze of space. The number of planetesimals in the early solar system was staggering. Simulations suggest trillions of kilometer-sized bodies populated the disk, along with countless smaller fragments. The space between them was not empty. It was a crowded, dynamic environment where collisions and gravitational encounters happened constantly. From this swarm, larger bodies would gradually emerge, sweeping up their smaller neighbors in a process that would take millions of years. Not all planetesimals survive to become planets. Many are destroyed in collisions, their fragments scattered across the disk. Others are flung outward by gravitational encounters, expelled from the inner system entirely. Still others fall into the sun, consumed by the star they once orbited. The survivors, the lucky few that grow rather than diminish, will become the cores of worlds. And so the disk transforms once again. Where once there was only dust, then pebbles, now there are mountains of rock and ice orbiting in the darkness. The streaming instability has bridged the gap that seemed unbridgeable. Gravity, patient and persistent, is ready to build something larger. The age of planetesimals has begun, and the age of planets is about to follow. With planetesimals scattered throughout the disk, a new phase of growth begins, one driven entirely by gravity. Larger bodies attract smaller ones. Collisions that once destroyed now build. Over millions of years, the countless planetesimals of the early disk will merge into a handful of worlds. This is the story of how rocky planets like Earth come to be. The first stage is called runaway growth. Among the swarm of planetesimals, some are slightly larger than others by chance. These larger bodies have stronger gravity, which gives them an advantage. They can attract planetesimals from a wider region of space, sweeping up material more efficiently than their smaller neighbors. The more they grow, the faster they grow. Success breeds success in a runaway process that quickly separates winners from the rest. During runaway growth, a few bodies pull dramatically ahead. A planetesimal that starts 10% larger than its neighbors might end up 10 times larger within a relatively short time. These emerging giants are called planetary embryos, objects roughly the size of our moon or the planet Mars. They dominate their local regions of the disk, having consumed most of the available planetesimals within their gravitational reach. The transition from runaway growth to the next stage is marked by a shift in dynamics. Once planetary embryos have swept up most nearby planetesimals, they begin to interact primarily with each other. Their feeding zones start to overlap. Growth slows as embryos compete for the remaining material. This phase is called oligarchic growth, rule by the few. A handful of embryos dominate the disk, each roughly similar in size, each jealously guarding its own orbital territory. During oligarchic growth, the inner disk might contain 20 or 30 planetary embryos, each perhaps a tenth of Earth's mass. They orbit in relative isolation, separated by gravitational boundaries that keep them apart. But this arrangement is not stable forever. Over tens of millions of years, gravitational perturbations accumulate. Orbits become eccentric. Eventually, embryos begin to cross each other's paths, and a new era of violent mergers begins. Giant impacts define the final stage of rocky planet formation. When two planetary embryos collide, the result is not destruction, but fusion. Two bodies becoming one, their combined mass forming a larger world. These collisions are catastrophic by any human measure. Entire surfaces are melted. Material is thrown into orbit. The energy released exceeds anything our planet has experienced in recorded history. And yet these impacts are the final steps in building a world. The heat from giant impacts transforms the growing planet. When an embryo-sized body strikes a proto-Earth, the energy deposited is enough to melt the entire surface and much of the interior. The planet becomes a magma ocean, a sphere of molten rock thousands of kilometers deep, glowing dull red against the blackness of space. In this state, heavy elements like iron and nickel sink toward the center, while lighter silicates float upward. This process of differentiation creates the layered structure of rocky planets: dense metal core, rocky mantle, thin crust. Radioactive elements also contribute to the heat. Elements like uranium, thorium, and potassium decay over time, releasing energy. In the early solar system, short-lived radioactive isotopes like aluminum-26 provided intense heating that helped melt the interiors of even small planetesimals. This radiogenic heat, combined with the energy of impacts, kept the interiors of growing planets molten for millions of years, allowing differentiation to proceed to completion. The timescale for rocky planet formation is measured in tens of millions of years. Our Earth reached roughly its current mass within 50 to 100 million years after the solar system began to form. This might seem long by human standards, but it is brief compared to the age of the solar system. The planet you rest upon tonight was essentially complete when the solar system was only 2% of its current age. The terrestrial planets of our solar system, Mercury, Venus, Earth, and Mars, all formed through this process. Each represents a different outcome of the same general sequence. Mercury, closest to the Sun, is small and dense, dominated by its iron core. Venus and Earth are similar in size, though their surfaces evolved very differently. Mars is smaller, a planetary embryo that never experienced the final giant impacts that might have made it larger. Why rocky planets form close to the star is a matter of temperature. Inside the frost line, only rock and metal can exist as solids. The total mass of solid material available for planet building is limited, perhaps 1 or 2% of the gas mass in this region. This sets an upper limit on how large rocky planets can grow. Earth is close to this limit, the largest rocky planet our solar system produced. Larger rocky worlds might exist around other stars, but they require unusual circumstances. The violence of the giant impact phase may seem at odds with the peaceful world we inhabit today, but that violence was creative, not destructive. Each impact mixed and melted, building rather than breaking. The world that emerged from this chaos was not a barren rock, but a planet with all the ingredients for oceans, atmosphere, and eventually life. The heat that seemed so destructive was actually the crucible in which a habitable world was forged. And so the rocky planets take their place in the inner solar system. Small, dense worlds built from the refractory materials that could survive close to the young sun. Their formation was complete while the disk still lingered in the outer regions, while gas giants were still gathering their vast atmospheres. The inner and outer solar system tell different stories, shaped by the same processes but playing out in different conditions. Beyond the frost line, a different kind of planet takes shape. Here, where ice adds to the inventory of solid material, larger cores can form. And if a core grows large enough, fast enough, it can begin to capture gas from the surrounding disk. Hydrogen and helium in quantities that dwarf the solid core beneath. This is how gas giants are born, and it is a race against time. The core accretion model explains how Jupiter and Saturn formed. First, a solid core assembles through the same processes that build rocky planets: planetesimals merging, embryos colliding, gravity gathering mass. But beyond the frost line, ice provides extra building material. A core can grow to 10 Earth masses or more, far larger than any rocky planet in the inner disk. This massive core becomes the seed of a gas giant. Once the core reaches a critical mass, roughly 10 times Earth's mass, something dramatic happens. The core's gravity becomes strong enough to hold onto hydrogen and helium gas from the surrounding disk. At first, gas accumulates slowly, building a thin atmosphere around the solid core. But as more gas arrives, the atmosphere grows heavier, compresses, and grows denser. Eventually, a threshold is crossed and gas begins to fall onto the planet in a runaway process. Runaway gas accretion transforms a super-Earth into a gas giant within a cosmically brief period, perhaps only a few 100,000 years. During this phase, the planet might double its mass every few centuries, gorging on the abundant hydrogen and helium that fills the disk. The solid core that started the process becomes buried beneath an ocean of gas, hundreds of times more massive than itself. The planet has become something entirely new. Jupiter is the supreme example of successful core accretion. Its core, buried deep beneath the swirling clouds, might contain 10 to 20 Earth masses of rock and ice, but this core represents only a few % of Jupiter's total mass. The rest is gas. Hydrogen compressed to metallic densities in the interior, helium mixed throughout, and the familiar banded clouds we see from Earth. Jupiter captured its atmosphere early and thoroughly, becoming the dominant planet of our solar system. Saturn followed a similar path, but with less spectacular results. Its core formed later or grew more slowly, and by the time it reached the critical mass for runaway accretion, the disk had already begun to dissipate. Saturn captured less gas than Jupiter, ending up with about a third of its giant neighbor's mass. Its lower density, Saturn would float in water if you could find a bathtub large enough, reflects this history. Less gas, more loosely held, gathered around a proportionally larger core. The timing of gas giant formation is crucial. The disk does not last forever. After a few million years, the gas begins to dissipate, blown away by stellar winds, absorbed by the star, or simply spreading into space. A core that reaches critical mass early can capture enormous amounts of gas. A core that arrives late finds little left to capture. The difference between a Jupiter and a Neptune may come down to nothing more than a few million years of timing. An alternative theory proposes that gas giants can form directly from the disk without building a core first. This disk instability model suggests that if a region of the disk becomes dense enough, it can collapse gravitationally, much like a star forming from a molecular cloud. The result would be a gas giant without a significant solid core, formed in thousands of years rather than millions. Disk instability may operate in unusual circumstances, in very massive disks, in the cold outer regions, or in disks around young stars that are still actively accreting material. Some directly imaged exoplanets, orbiting far from their stars, might have formed this way. But for the gas giants of our own solar system, core accretion remains the favored explanation, supported by evidence that both Jupiter and Saturn possess dense cores beneath their gaseous exteriors. The composition of gas giants reveals their origin. Hydrogen and helium dominate, as they dominated the original disk. But gas giants also contain heavier elements: water, ammonia, methane, and silicates, in proportions greater than the Sun's. These enrichments suggest that the planets incorporated substantial amounts of solid material, either as their initial cores or as planetesimals captured during their growth. Gas giants are not pure gas, but mixtures, bearing the signatures of their complex formation. Inside a gas giant, conditions become extreme. At the center of Jupiter, pressures reach millions of atmospheres and temperatures exceed 20,000 degrees. Under these conditions, hydrogen behaves like a metal, conducting electricity and generating the powerful magnetic field that surrounds the planet. The interior is alien beyond imagination. A sea of metallic hydrogen surrounding a core of compressed rock and ice, all hidden beneath the colorful clouds that mark the visible surface. The formation of gas giants reshapes the entire planetary system. Their gravity influences the orbits of everything nearby. They scatter planetesimals, some inward to bombard the rocky planets, some outward to populate the distant reaches of the system. They carve gaps in the disk, blocking the flow of material. They may cause other planets to migrate. Gas giants are not passive inhabitants of their systems, but active shapers of planetary architecture, and so Jupiter and Saturn took their places in the outer solar system. Massive worlds born from the marriage of solid cores and captured gas. Their presence would dominate the evolution of our solar system for billions of years to come. But they were not the only giants to form beyond the frost line. Farther out, in the colder and more distant regions of the disk, a different kind of giant was taking shape. Uranus and Neptune are often grouped with Jupiter and Saturn as giant planets, but they are fundamentally different. While Jupiter and Saturn are gas giants, dominated by hydrogen and helium, Uranus and Neptune are ice giants, worlds where water, ammonia, and methane form the bulk of the mass beneath relatively thin, gaseous envelopes. Their formation tells a distinct story. The ice giants began the same way as the gas giants, with solid cores growing through accretion of planetesimals. Beyond the frost line, ice was abundant, providing ample building material. Cores grew steadily, accumulating rock and frozen volatiles over millions of years. But something prevented these cores from triggering the runaway gas accretion that made Jupiter and Saturn so massive. The most likely explanation is time. In the outer disk, where Uranus and Neptune formed, orbital periods are measured in decades rather than years. Everything happens more slowly. Planetesimals take longer to collide. Cores take longer to grow. By the time the ice giant cores reached the critical mass for rapid gas accretion, the disk had already begun to fade. There was simply not enough gas left to capture in large quantities. The result is planets dominated by their original icy cores, rather than their gaseous atmospheres. Neptune has a mass of about 17 Earths. Of this, perhaps 1 or 2 Earth masses is hydrogen and helium atmosphere. The rest is rock and ice, water, ammonia, and methane compressed to extraordinary densities deep in the interior. These planets are more closely related to the comets of the outer solar system than to the gas giants that preceded them. The composition of ice giant atmospheres gives them their distinctive appearance. Methane in the upper atmosphere absorbs red light, giving both Uranus and Neptune their beautiful blue-green hues. Neptune's deeper blue suggests a more dynamic atmosphere, with more methane and more vigorous weather. Uranus is paler, its atmosphere more subdued, tilted strangely on its side by some ancient collision. Inside the ice giants, conditions are unlike anything else in the solar system. Beneath the visible clouds lies an ocean, not of water as we know it, but of water, ammonia, and methane compressed to fluid densities at temperatures of thousands of degrees. This exotic mixture behaves like neither liquid nor gas, but something in between, conducting electricity and convecting heat from the deep interior to the surface. Deeper still, the pressures become so extreme that molecules are crushed and reformed. Methane molecules are squeezed until their carbon atoms separate and bond together. Computer simulations suggest that diamond crystals form in these conditions, literal diamonds precipitating out of the interior and falling through the mantle like rain. Diamond rain is one of the most extraordinary possibilities in planetary science, a phenomenon that may occur continuously deep within Uranus and Neptune. The positions of Uranus and Neptune today may not reflect where they formed. Several lines of evidence suggest that these planets originally formed closer to the Sun, perhaps in the region between Saturn and where the Kuiper Belt now begins. Gravitational interactions with the gas giants and with the remaining disk of planetesimals pushed them outward over hundreds of millions of years. Their current distant orbits are the result of migration, not birth. Neptune's largest moon, Triton, provides a clue to this violet history. Triton orbits Neptune backward, opposite to the planet's rotation, which means it cannot have formed alongside Neptune. Instead, Triton must have been captured, perhaps from the Kuiper Belt, during a close encounter. The energy required to capture Triton would have dramatically altered its orbit and possibly contributed to the disruption of an earlier moon system. Neptune's past was not peaceful. Ice giants may be among the most common type of planet in the galaxy. Surveys of exoplanets have revealed numerous worlds with masses between Earth and Neptune, so-called sub-Neptunes and mini-Neptunes that have no equivalent in our solar system. These worlds might be ice giants or smaller versions of them, common outcomes of planet formation around other stars. Our own ice giants might be relatively modest examples of a widespread planetary type. The formation of Uranus and Neptune completes the architecture of the outer solar system. 4 giant planets, 2 dominated by gas and 2 by ice, orbiting beyond the frost line where volatile compounds could survive as solids. But this arrangement was not the end of the story. The giant planets did not remain fixed in their orbits. Gravity continued to shape the solar system, pushing and pulling, rearranging what had seemed settled. The age of migration was about to begin. Planets are born in one place, but do not always stay there. The gravitational forces that build worlds can also move them, shifting orbits over millions of years, rearranging the architecture of entire planetary systems. This process of migration has shaped our solar system in profound ways and may explain some of its most puzzling features. Migration begins in the disk itself. A planet embedded in a protoplanetary disk does not orbit in isolation. It interacts gravitationally with the gas and dust around it. These interactions can exchange angular momentum between the planet and the disk, causing the planet's orbit to shrink or expand. A planet might drift inward toward the star or outward toward the disk's edge, depending on the balance of forces involved. The details of disk-driven migration depend on the planet's mass. Small planets, not massive enough to clear gaps in the disk, experience Type 1 migration. They drift through the disk like boats through water, pushed by the cumulative gravitational tugs of the gas around them. Type 1 migration is typically inward and can be rapid. A Mars-sized body might spiral into the inner disk within 1 million years if nothing stops it. Larger planets, massive enough to carve gaps in the disk, experience Type 2 migration. Here, the planet clears a ring of empty space in the disk material around its orbit. Migration occurs as the disk itself evolves. As material flows inward onto the star, it drags the planet along. Type 2 migration is slower than Type 1, but can still move giant planets substantial distances over the lifetime of the disk. Jupiter's migration may have profoundly shaped our solar system. One influential model, called the Grand Tack, proposes that Jupiter formed at about 3 times Earth's distance from the Sun, then migrated inward as far as the orbit of Mars today. Only when Saturn grew large enough did the two giants become locked in a gravitational resonance that reversed the migration, sending both planets back outward to roughly their current positions. If the Grand Tack occurred, it would explain several puzzles. The small mass of Mars might result from Jupiter's gravity depleting the Mars-forming region of material. The asteroid belt's current structure, rocky asteroids mixed with more primitive water-rich types, might reflect the stirring caused by Jupiter's passage. The delivery of water to Earth might trace back to material scattered inward during this migration. One giant planet's journey could explain much about the inner solar system's architecture. After the disk dissipated, migration continued through different mechanisms. The outer solar system remained populated by countless planetesimals, remnants of planet formation that never coalesced into larger bodies. Gravitational encounters between planets and these small bodies exchanged energy and angular momentum, gradually shifting planetary orbits over hundreds of millions of years. The Nice model describes what may have happened next. According to this scenario, the 4 giant planets were originally more compact, with their orbits closer together and closer to the Sun. Beyond them lay a massive disk of icy planetesimals, precursors to today's Kuiper Belt. Over hundreds of millions of years, gravitational interactions scattered these planetesimals, and the orbits of the giant planets slowly adjusted in response. At some point, the system became unstable. Jupiter and Saturn crossed a critical orbital resonance, triggering a cascade of gravitational chaos. Uranus and Neptune were flung outward into the planetesimal disk, scattering small bodies in all directions. Some were sent inward, bombarding the inner solar system in an event called the Late Heavy Bombardment. Others were flung outward, populating the scattered disk beyond Neptune. The solar system was transformed. Evidence for the Late Heavy Bombardment comes from the ancient surfaces of the Moon and other bodies. Craters dated to roughly 4 billion years ago are far more numerous than expected from a steadily declining bombardment rate. Something caused a spike in impacts at this time, and the instability predicted by the Nice model would produce exactly such a spike. The battered face of the Moon may record the scars of giant planet migration. Migration is not unique to our solar system. Observations of exoplanets reveal systems where giant planets orbit astonishingly close to their stars. The famous hot Jupiters that complete an orbit in just a few days. These planets could not have formed where they now reside. The heat of the nearby star would have prevented gas accumulation. Instead, they must have formed farther out and migrated inward, perhaps through the disk, perhaps through gravitational scattering by other planets. Some planetary systems show evidence of dramatic reorganization. Multiple planets might be locked in chains of resonances, the gravitational signature of migration, preserving their history like fingerprints. Other systems seem chaotic, with planets on highly elliptical or inclined orbits that hint at past instabilities. Every planetary system carries the marks of its dynamic past. Migration means that the planets we see today are not necessarily where they began. The neat arrangement of rocky planets close to the sun and giants farther out is not inevitable but contingent, the result of specific conditions and specific histories. Planets that formed in order might have been reshuffled. Planets that started close might have moved far. The solar system's current architecture is just one frame in a 4 billion-year story. This realization adds depth to our understanding of our own world. Earth did not simply form where it is and stay put. It survived a period of chaos when giant planets were on the move, when the inner solar system was being bombarded by scattered debris, when orbits were shifting and nothing was certain. Our planet's existence is not just a matter of the right ingredients in the right place. It is also a matter of surviving the dynamic adolescence of a young planetary system. And so the planets found their places, not through stillness, but through motion, not through stability, but through upheaval. The solar system we know is the calm after a storm that lasted hundreds of millions of years. The worlds have settled into their orbits, and the long quiet era that allowed life to emerge on Earth has stretched for billions of years. But the memory of migration is written in the very arrangement of the planets, in the structure of the asteroid belt, in the scattered objects of the outer solar system. Planets are not always alone. Many are accompanied by moons, smaller worlds bound in gravitational embrace, circling their parent planets as the planets circle their stars. The moons of our solar system are astonishingly diverse, ranging from tiny irregular rocks to worlds larger than some planets with atmospheres, oceans, and geology of their own. Each moon has an origin story, and those stories are as varied as the moons themselves. Moons can form in several ways. Some are born alongside their planets, coalescing from the same disk of material that built the planet itself. Others are wanderers, captured from elsewhere by a planet's gravity. Still others are created in violence, blasted into existence by catastrophic collisions that reshape both worlds involved. The moons we see today preserve the records of these different origins, frozen in their orbits and compositions. The large moons of Jupiter likely formed through co-accretion, the same process that built the planets, but in miniature. As Jupiter grew, it was surrounded by its own disk of gas and dust, a smaller version of the protoplanetary disk around the Sun. Within this circumplanetary disk, material accumulated into moonlets, which merged into larger bodies. The 4 Galilean moons, Io, Europa, Ganymede, and Callisto, are the survivors of this process, worlds that formed in orbit around their giant parent. The composition of Jupiter's moons reflects their birthplace within the circumplanetary disk. Io, closest to Jupiter, is rocky and volcanic. Its volatiles, long since baked away by the heat of formation and the intense radiation environment. Europa, farther out, retained enough water to form a global ice shell, and possibly an ocean beneath. Ganymede and Callisto, more distant still, are mixtures of rock and ice in roughly equal proportions. The temperature gradient of the disk determined what each moon could become. Saturn's rings and moons tell a more complex story. Some moons appear ancient, survivors from Saturn's formation. Others seem younger, perhaps created more recently from the destruction of earlier bodies, or from material shed by the rings themselves. The rings themselves may be the remains of a moon torn apart by tidal forces, or the debris of a comet that wandered too close. Saturn's system is a puzzle with pieces still being assembled. Capture is another path to moonhood. When a small body passes close to a planet, gravitational interactions can steal enough energy to trap the object in orbit. This requires special circumstances: the presence of an atmosphere to provide drag, a third body to absorb the excess energy, or an extended disk of material to slow the intruder. But when conditions align, a passing wanderer can become a permanent companion. Mars's two moons, Phobos and Deimos, may be captured asteroids. Their small sizes, irregular shapes, and dark compositions resemble objects from the asteroid belt more than debris from Mars itself. However, their nearly circular equatorial orbits are difficult to explain through simple capture. They may have been captured into an initial disk that subsequently formed the moons we see today. The question of their origin remains open, a small mystery orbiting a small planet. Neptune's largest moon, Triton, is almost certainly a captured world. Its retrograde orbit, moving opposite to Neptune's rotation, cannot result from formation within a circumplanetary disk. Triton must have originated elsewhere, probably in the Kuiper belt, before a close encounter with Neptune trapped it in orbit. The capture would have been violent, generating enormous tidal heating that may have kept Triton's interior warm for billions of years. Even today, Triton shows signs of geological activity. Geysers of nitrogen erupting from its frozen surface. The most dramatic moon formation mechanism is giant impact. When two planetary bodies collide, the debris ejected into orbit can coalesce into one or more moons. This process requires a specific kind of impact, not a direct hit that simply merges the two bodies, but a glancing blow that throws material into orbit while leaving both bodies partially intact. The geometry must be just right, but when it happens, the results can be spectacular. Our own moon was born in such a collision. About 4.5 billion years ago, when Earth was still young and largely molten, a Mars-sized body struck our planet at an oblique angle. The impactor, often called Theia, was destroyed. A significant portion of both Theia and Earth's mantle was vaporized and thrown into orbit. From this ring of superheated debris, the moon coalesced within perhaps a century. A new world born from destruction. The evidence for the giant impact hypothesis is compelling. Moon rocks brought back by the Apollo astronauts have oxygen isotope ratios nearly identical to Earth's, far more similar than meteorites from Mars or the asteroid belt. This suggests that the moon formed primarily from Earth material, mixed perhaps with material from Theia. The moon's low density and small iron core makes sense if it formed mostly from Earth's mantle, which is poor in iron compared to the core. The moon that emerged from this cataclysm was far closer than the moon we see today. Initially orbiting perhaps 15 times closer than its current distance, the young moon loomed enormous in Earth's sky, a brilliant, tidally locked companion that raised towering tides in Earth's molten surface. Over billions of years, tidal interactions have slowly pushed the moon outward, trading rotational energy from Earth for orbital distance. The moon recedes from Earth by about 4 centimeters per year, even now. The stabilizing influence of the moon may have been crucial for Earth's habitability. Earth's axial tilt, the inclination that gives us seasons, remains relatively stable because of the moon's gravitational influence. Without the moon, Earth's axis might wobble chaotically over millions of years, producing wild swings in climate that could make the evolution of complex life far more difficult. Our companion world may be more than a beautiful presence in the night sky. It may be one reason we are here at all. Pluto and its moon Charon may also be the products of a giant impact. Charon is unusually large compared to Pluto, about half Pluto's diameter, making it the largest moon relative to its planet in the solar system. The two bodies are tidally locked to each other, always showing the same face, orbiting their common center of mass like a double world. This configuration is consistent with an origin in a violent collision between two Kuiper belt objects billions of years ago in the cold outer reaches of the solar system. The diversity of moons across the solar system reflects the diversity of processes that create them. Some are born gently, from disks of gas and dust. Some are seized from passing trajectories. Some are blasted into existence by collisions that reshape worlds. Each moon carries the signature of its origin, waiting to be read by spacecraft and telescopes. In studying moons, we study the many ways that worlds can come to be. Among all the planets in our solar system, Earth's birth holds special significance. This is the world we call home, the planet whose history is our history. Understanding how Earth formed is understanding our own deepest origins, the cosmic processes that created the ground beneath our feet and the air we breathe. It is a story of fire and stone, of bombardment and transformation, of violence giving way to the calm that allowed life to emerge. Earth began as countless others did, as dust grains sticking together in the inner regions of the protoplanetary disk. Close to the young sun, only rock and metal could exist as solids. The temperatures were too high for ice, too high for volatile compounds. The building blocks of Earth were refractory: silicates, iron, nickel, and traces of other elements that could withstand the heat. From these materials, planetesimals formed, then embryos, then a growing world. The early Earth was a violent place. Planetesimals rained down continuously, each impact adding mass and energy. The surface was molten, a global magma ocean glowing dull red beneath a sky thick with vaporized rock. There was no solid ground, no oceans, no atmosphere as we would recognize it. The planet was a crucible, constantly stirred by impacts, its interior churning with convective heat. During this magma ocean phase, Earth's internal structure took shape. Heavy elements, primarily iron and nickel, sank toward the center, forming the planet's dense metallic core. Lighter silicate minerals floated upward, forming the mantle and eventually the crust. This process of differentiation separated Earth into distinct layers, each with its own composition and properties. The core, mantle, and crust that define Earth's structure today were established in those first few 100 million years. The formation of the core released enormous amounts of gravitational energy, adding to the heat generated by impacts and radioactive decay. The early Earth was far hotter than it is today, its interior so warm that the mantle may have been entirely molten rather than the slowly flowing solid it is now. This heat has been leaking away ever since, driving the plate tectonics that reshapes Earth's surface and generates the magnetic field that shields us from harmful radiation. Then came Theia. About 50 million years after Earth began to form, a body roughly the size of Mars collided with our young planet. The impact was oblique, a glancing blow rather than a head-on collision. The energy released was almost unimaginable, enough to remelt Earth's entire surface, vaporize much of both worlds, and throw a disk of debris into orbit. From that debris, as we have seen, the moon was born. Earth emerged from the collision larger, hotter, and forever changed. After the moon-forming impact, Earth entered a period of relative calm. Though calm by the standards of planetary formation, still meant frequent bombardment by leftover debris. The magma ocean gradually cooled, forming a solid crust that was repeatedly punctured and remelted by incoming impacts. Volcanic outgassing released gases from the interior, water vapor, carbon dioxide, nitrogen, that began to accumulate as a primitive atmosphere. The origin of Earth's water remains a subject of debate. Some water may have been present in the dust grains that built the planet, trapped in minerals and released during differentiation. Some may have arrived later, delivered by asteroids and comets from the outer solar system. The relative contributions of these sources are still being investigated, but both probably played a role. The oceans that would eventually cover much of Earth's surface have complex origins, gathered from multiple sources over hundreds of millions of years. A period of intense bombardment may have occurred around 700 million years after the solar system formed. This late heavy bombardment, if it occurred as a distinct event, would have sterilized Earth's surface repeatedly, preventing any life that might have begun from gaining a permanent foothold. The evidence for this bombardment comes primarily from lunar crater counts and the ages of lunar samples. Whether it was a sudden spike or a gradual decline in impacts remains debated, but either way, the early Earth was a dangerous place. Gradually, conditions changed. The bombardment rate declined as the solar system cleared out its remaining debris. Earth's surface cooled enough for water to condense, first as rain falling on hot rock and immediately evaporating, then accumulating in low-lying areas to form the first seas. The atmosphere evolved, its composition shifting as volcanic gases accumulated and chemical reactions proceeded. Earth was becoming habitable. The first continents emerged from the global ocean perhaps 4 billion years ago, though the timing and mechanism remain uncertain. These early landmasses were not the continents we know today, but smaller, more primitive structures. Proto-continents of volcanic rock rising above the waves. Over billions of years, plate tectonics would build, break, and rebuild continents, shuffling the pieces of Earth's surface in an endless, slow dance. Earth's magnetic field established itself early, generated by convection currents in the liquid outer core. This invisible shield deflects the solar wind, the stream of charged particles flowing outward from the sun, protecting the atmosphere from being stripped away. Mars, lacking a global magnetic field, lost much of its atmosphere to space. Earth's magnetism is one reason our planet retained the air and water that make life possible. The moon continued to influence Earth's evolution. Tidal forces slowed Earth's rotation, lengthening the day from perhaps 6 hours to the 24 hours we know today. The tides themselves may have played a role in the origin of life, creating pools where chemicals could concentrate and react. The moon stabilized Earth's axial tilt, preventing the wild climate swings that might have made complex life impossible. Our companion world has been shaping our planet since its violent birth. By about 4 billion years ago, Earth had become recognizable. A blue world with oceans and continents, an atmosphere rich in nitrogen and carbon dioxide, a magnetic field shielding it from space, a moon steadily receding in the sky. The planet was ready for life. Within a few 100 million years, perhaps sooner, the first living things would appear in Earth's waters. The story of our planet was just beginning. Built on a foundation of cosmic violence, transformed into cosmic opportunity. For most of human history, we knew of only the worlds in our own solar system, a handful of planets orbiting a single star, the only examples of planetary existence we could study. That changed in 1992 when astronomers discovered the first planets orbiting another star. Since then, thousands of exoplanets have been confirmed, revealing a universe far richer and stranger than anyone had imagined. Worlds are everywhere. The first exoplanets discovered were found around a pulsar, a rapidly spinning neutron star, the collapsed remnant of a massive star that exploded as a supernova. These planets orbit in an environment utterly hostile to life, bathed in intense radiation, likely formed from the debris of the supernova itself. Their discovery showed that planet formation is robust, capable of occurring even in the most extreme circumstances. The first exoplanet, found around a sun-like star, was 51 Pegasi b, detected in 1995 by Swiss astronomers Michel Mayor and Didier Queloz. This world shocked the scientific community. It was a gas giant, roughly half the mass of Jupiter, but it orbited its star in just 4 days, at a distance far closer than Mercury orbits our Sun. Such a world had no equivalent in our solar system. It could not have formed where it now resides. The era of exoplanet surprises had begun. Worlds like 51 Pegasi b came to be called hot Jupiters, gas giants that have somehow ended up in tight, scorching orbits around their stars. Their surfaces, if they have surfaces, would be heated to thousands of degrees. Some orbit so close that they are being slowly evaporated by stellar radiation, their atmospheres streaming away into space. These worlds must have formed farther out and migrated inward, their journeys rewriting our understanding of how planetary systems evolve. The Kepler Space Telescope, launched in 2009, transformed exoplanet science. By staring at a single patch of sky and watching for the tiny dimming of stars as planets passed in front of them, Kepler discovered thousands of worlds. Its data revealed that planets are common. Most stars have at least one, and many have several. The galaxy contains more planets than stars, billions upon billions of worlds waiting to be studied. Among Kepler's discoveries was an entirely new class of planet, worlds between Earth and Neptune in size, with no analog in our solar system. These super-Earths and mini-Neptunes are actually the most common type of planet in the galaxy. Some may be rocky worlds with thick atmospheres. Others may be water worlds, ocean planets with no dry land. Still others may be small gas planets, failed Neptunes that never grew large enough to dominate their systems. We are still learning what these worlds are like. The TRAPPIST-1 system, discovered in 2016, captured the public imagination. This small, cool red dwarf star hosts 7 Earth-sized planets, all orbiting closer to their star than Mercury orbits the Sun. 3 of these worlds lie in the habitable zone, where liquid water could potentially exist on their surfaces. The planets are so close together that if you stood on one, the others would appear as large as the moon, or even larger in the sky. A system of sister worlds, each potentially visible from the others. The James Webb Space Telescope, launched in 2021, has begun to analyze the atmospheres of exoplanets. By measuring the starlight that filters through a planet's atmosphere during transit, Webb can detect the chemical fingerprints of molecules like water, carbon dioxide, and methane. Early results have revealed atmospheres around several worlds, some with unexpected compositions. We are taking the first steps toward understanding not just where exoplanets are, but what they are made of. Direct imaging of exoplanets remains challenging, but increasingly possible. Young massive planets that still glow with the heat of formation can be photographed as points of light near their parent stars. The HER 8799 system, about 130 light-years from Earth, contains 4 directly imaged giant planets, each several times Jupiter's mass. Watching these worlds over years, astronomers can track their orbital motion. Dots of light slowly circling a distant sun, direct evidence of other solar systems in motion. The diversity of exoplanetary systems has shattered old assumptions. Some systems have planets packed into resonant chains, their orbits interlocked by gravity. Others have planets on highly elliptical paths, swooping close to their stars and then retreating to the outer darkness. Some have planets orbiting in the opposite direction of their star's rotation. Some have planets orbiting binary stars with 2 suns in their skies. The orderly arrangement of our solar system is just one possibility among many. Some exoplanets orbit in the habitable zones of their stars, regions where temperatures might allow liquid water to exist. These worlds are prime targets in the search for life beyond Earth. Rocky planets like TRAPPIST-1e and Proxima Centauri b orbit in their stars' habitable zones, tantalizing possibilities for worlds where life might have gained a foothold. We do not yet know if any of these worlds are truly Earth-like, but the search has never been more promising. The statistics are staggering. Based on Kepler data, astronomers estimate that there are at least 100 billion planets in our galaxy alone. Perhaps 20 billion of these are Earth-sized worlds in the habitable zones of their stars. And there are hundreds of billions of galaxies in the observable universe, each with its own population of planets. The universe is not a sparse scattering of isolated worlds, but a cosmic garden, abundant with planets beyond counting. Each exoplanet represents a different outcome of the processes we have explored. Different initial conditions, different histories, different fates. Some formed quickly, others slowly. Some migrated, others stayed put. Some were ejected from their systems entirely. In studying exoplanets, we see the full range of what planet formation can produce. Our solar system, once the only example we knew, is now one case study among thousands, a single data point in a vast census of worlds. Not all planets orbit stars. Some drift alone through the galaxy, unbound to any sun, wandering the darkness between stellar systems. These rogue planets, ejected from their birthplaces by gravitational chaos, represent one of the strangest outcomes of planet formation. Untethered and solitary, they voyage through the cosmos in eternal night. Rogue planets are created through violence. When multiple planets form in a system, their gravitational interactions can become chaotic. Close encounters transfer energy from one orbit to another. Eventually, one planet may gain enough energy to escape the star's gravitational hold entirely. It is flung outward, leaving its siblings behind, beginning a journey that will never end. The process is surprisingly common. Simulations of planetary system formation suggest that many systems produce more planets than they keep. For every planet that settles into a stable orbit, one or more might be ejected. The galaxy may contain billions of rogue planets, perhaps more rogue planets than stars. These invisible wanderers drift through interstellar space, outnumbering the worlds that remain bound to their suns. Detecting rogue planets is enormously difficult. They emit no light of their own, at least none visible to ordinary telescopes. They do not transit stars. They cannot be found through the wobble method, used to detect planets around other suns. They are dark objects moving through a dark void, revealing themselves only through their gravitational effects. Microlensing offers a way to find rogue planets. When a massive object passes between Earth and a distant star, its gravity bends and focuses the star's light, causing a brief brightening. The duration and shape of this brightening reveal the mass of the lensing object. Several candidate rogue planets have been detected this way. Fleeting brightenings that suggest Earth mass or Jupiter mass objects drifting through the galaxy. A rogue planet is not necessarily a dead world. Even without a star, a planet might retain internal heat, warmth from radioactive decay in its core, residual heat from its formation, or tidal heating if it carries moons of its own. This heat could maintain a liquid layer beneath an icy surface, a subsurface ocean hidden from the frozen vacuum above. Life, if it can exist without sunlight, might find a refuge on worlds we would never think to search. The surface of a rogue planet would be cold beyond imagination. Without a star to warm it, any atmosphere would freeze and fall as snow. Surface temperatures might drop to just a few degrees above absolute zero. The planet would be a dark sphere, invisible against the black of space. Its only light, the faint glow of distant stars. It is a lonely existence, a world forever cut off from the warmth that nurtures life as we know it. Some rogue planets may be larger than Jupiter. These super-Jupiters blur the line between planet and failed star. If massive enough, their cores might briefly fuse deuterium, a form of hydrogen, in a process that generates some heat but falls far short of true stellar ignition. These objects are called brown dwarfs by some and massive planets by others. The boundary between planet and star is not as clear as it might seem. Rogue planets could theoretically be captured by other stars. A planet wandering too close to a stellar system might lose enough energy through gravitational interactions to become bound. Such a planet would be an immigrant, a world born around one star and adopted by another. The process is rare, but over the history of the galaxy, some adopted planets may exist. Worlds whose birthplaces are not the systems they now call home. The existence of rogue planets adds a poignant dimension to the story of planet formation. Not every world gets to stay. Not every planet finds a stable orbit where it can remain for billions of years. Some are expelled, cast out to wander forever. The galaxy is home not only to the planets we can see, orbiting their stars in orderly fashion, but also to an unseen population of exiles, worlds without suns, drifting through the endless night. We have traced the journey from dust to worlds, from molecular clouds to fully formed planets. But not everything in the solar system completed that journey. Scattered among the planets are objects that almost became worlds, but never quite arrived. Failed planets, leftover building blocks, frozen remnants of the formation process. These objects are not failures in any meaningful sense. They are witnesses, preserving conditions and materials from the earliest times. The asteroid belt represents the most famous example of a failed planet. Between Mars and Jupiter lies a region populated by millions of rocky bodies, ranging from dust-sized particles to the dwarf planet Ceres, nearly 1,000 kilometers across. Early in solar system history, this region contained enough material to build a small planet. But that planet never formed. Jupiter is responsible. As Jupiter grew massive in the outer solar system, its gravity stirred the asteroid belt violently. planetesimals that might have merged were instead scattered or destroyed. The gentle process of accretion was replaced by constant disruption. Objects collided at high speeds, shattering rather than sticking. The belt was prevented from ever coalescing into a single world. Ceres is the largest object in the asteroid belt, so large that it is classified as a dwarf planet rather than an asteroid. With a diameter of about 940 kilometers, Ceres contains roughly a third of the asteroid belt's total mass. It is differentiated with a rocky core and an icy mantle, and may harbor a subsurface ocean of liquid water. Ceres is the closest thing the asteroid belt has to a completed world, a planetary embryo that never grew further. The asteroid belt today contains only a tiny fraction of the material that once filled this region. Most of the original mass was either ejected from the solar system, fell into the sun, or was swept up by the inner planets during the period of heavy bombardment. What remains is perhaps 1/1000th of what was once there, a remnant population thinned by 4 billion years of gravitational erosion. Beyond Neptune lies another realm of remnants, the Kuiper Belt. This donut-shaped region extends from Neptune's orbit outward to perhaps 50 astronomical units from the Sun. It contains hundreds of thousands of icy bodies larger than 100 kilometers across, and millions of smaller objects. These are the leftover planetesimals of the outer solar system, preserved in the deep freeze of distant space. Pluto is the most famous Kuiper Belt object, though it was discovered long before the belt itself was recognized. Once considered the 9th planet, Pluto is now classified as a dwarf planet, one of several large worlds in the Kuiper Belt that share similar orbits and compositions. Pluto's demotion was not a slight, but a recognition that the outer solar system contains an entire population of comparable objects, not just one special world. The Kuiper Belt preserves material from the earliest times of solar system formation. These icy bodies have been stored at temperatures so low that even volatile compounds remain frozen. Studying Kuiper Belt objects is like examining time capsules, samples of the primordial material from which the outer planets formed, preserved nearly unchanged for 4.6 billion years. Some objects were scattered outward by Neptune's migration, forming what is called the scattered disk. These bodies have highly elliptical orbits, swooping from near Neptune's distance out to hundreds of astronomical units from the Sun. They are more disturbed than the classical Kuiper Belt, their orbits marking them as survivors of gravitational encounters with the ice giant. Even farther out lies the Oort cloud, a theoretical sphere of icy bodies extending perhaps halfway to the nearest star. The Oort cloud has never been directly observed, but its existence is inferred from the orbits of long-period comets, which fall inward from this distant reservoir. If the Oort cloud exists as predicted, it contains trillions of icy bodies, planetesimals ejected during the chaotic early evolution of the solar system, now orbiting in the cold darkness at the very edge of the Sun's gravitational reach. Near-Earth asteroids remind us that the remnants of formation are not only distant. Thousands of asteroids have orbits that bring them close to Earth, some crossing our planet's path. These objects are dynamically unstable, destined to eventually collide with a planet or be ejected from the inner solar system. They are constantly replenished from the main belt by gravitational perturbations and collisions. The building blocks of planets are still with us, still occasionally visiting the worlds they help to build. The line between planet and non-planet is drawn by humans, not by nature. Ceres, Pluto, and other dwarf planets completed the same processes as the larger worlds: accretion, differentiation, possibly even geological activity. They are planets in all but designation, worlds that simply didn't grow as large as their neighbors. The solar system is not divided into planets and debris, but spans a continuum of sizes, from dust grains to Jupiter, each object representing a different stage or outcome of the same grand process. These remnants and near misses complete our picture of planetary formation. Every asteroid, every comet, every frozen body in the outer darkness is a piece of the original puzzle. Together, they show us what the raw materials looked like, how the process unfolded, and what was left behind. The planets did not form in isolation, but emerged from a sea of smaller objects, some of which survived to tell the tale. The birth of a planet is not a single event, but a sequence of transformations, each unfolding on its own timescale. From the first stirring of a molecular cloud to the final settling of a mature world, the process spans hundreds of millions of years. To understand planetary formation is to understand deep time, intervals so vast that they challenge human comprehension, yet so brief compared to the age of the universe that planets can form again and again across cosmic history. The collapse of a molecular cloud into a protostar and disk takes roughly 100,000 to 1 million years. This might seem long by human standards, but it is remarkably fast for an astronomical process. A cloud that drifted unchanged for 10 million years can transform into a star surrounded by a spinning disk in less than 1/100th of that time. Gravity, once it takes hold, works with surprising speed. The growth of dust into pebbles proceeds over the next few 100,000 years. Tiny grains, colliding gently in the disk, accumulate into larger aggregates through processes we have already explored. By the time the protostar ignites and becomes a true star, the disk surrounding it is already filled with particles ranging from dust to centimeter-sized pebbles. The raw materials for planets are assembling even as the star itself is being born. The leap from pebbles to planetesimals, the streaming instability and gravitational collapse we discussed earlier, happens relatively quickly once conditions are right. Dense clumps of pebbles can collapse into kilometer-sized bodies within centuries, or even less. This rapid formation means that planetesimals appear early in the disk's lifetime, while plenty of gas and dust remain for further growth. The building blocks of planets are in place within the first million years. Gas giant formation must occur within the lifetime of the disk, typically 3 to 10 million years. After this period, the gas that makes up the bulk of a Jupiter or Saturn will have dissipated, blown away by stellar radiation, or accreted onto the star. A core that reaches critical mass early can capture an enormous atmosphere. A core that arrives late finds nothing left to capture. The race against time determines whether a planetary system will have gas giants or not. Rocky planet formation is more leisurely. Because rocky planets do not require gas capture, they can continue growing long after the disk has dispersed. The giant impact phase, when planetary embryos collide and merge into final planets, extends for tens of millions of years, perhaps even 100 million years. Earth reached approximately its current mass within 50 to 100 million years after the solar system began to form, but the final impacts that shaped our world may have continued for longer still. The moon-forming impact occurred roughly 50 million years after the solar system's birth. This single event, lasting perhaps hours in its most violent phase, reshaped Earth's future for billions of years. The debris disk that surrounded Earth after the impact coalesced into the moon within perhaps a century. A brief moment of rapid formation following the catastrophic collision. Violence and creation intertwined in a span of time barely longer than a human lifetime. The late heavy bombardment, if it occurred as a distinct event, peaked around 700 million years after the solar system formed. This spike in impacts may have lasted for 100 million years or more, pummeling the surfaces of the inner planets and resetting the geological clocks of ancient rocks. The moon's cratered face preserves the record of this bombardment, a surface battered by the final convulsions of planetary rearrangement. The full settling of the solar system, planets finding stable orbits, the clearing of debris, the establishment of the architecture we see today, took perhaps 1 billion years. Even then, the system continued to evolve. Asteroids still migrate slowly under gravitational influences. Comets still fall inward from the outer darkness. The solar system is not static but dynamic, still changing after 4.6 billion years, though far more slowly than in its violent youth. Radiometric dating allows us to reconstruct these timescales with remarkable precision. By measuring the decay of radioactive elements in meteorites and lunar samples, scientists can determine when specific events occurred. The oldest dated solids in the solar system, calcium-aluminum-rich inclusions in primitive meteorites, formed 4.567 billion years ago, marking the beginning of the story. Everything since can be measured against this starting point. The timescales of planetary formation are simultaneously brief and vast. Brief compared to the age of the universe, the entire process from cloud collapse to mature planet takes less than 1% of cosmic time. Vast compared to human experience, 1 million years is longer than our species has existed, and planet formation requires tens or hundreds of millions. We must stretch our minds to grasp these intervals, accepting that nature operates on schedules far different from our own. And yet the universe has had time enough. In 13.8 billion years, countless generations of stars have formed and died, each generation seeding the next with heavier elements. Planet formation has occurred again and again, around stars that burned out before our sun was born, around stars shining now in distant galaxies, around stars that will not form for billions of years yet. The timescales are long, but the universe is patient. We are not limited to studying our own solar system's past. Right now, around young stars scattered across the galaxy, planets are being born. With modern telescopes, we can observe these processes in action. Protoplanetary disks swirling with dust, gaps being carved by unseen planets, young worlds glowing with the heat of their formation. We are witnesses to creation, watching other solar systems take shape in real time. The Atacama Large Millimeter Array, ALMA, has revolutionized our view of planet-forming disks. This collection of radio telescopes in the Chilean desert can peer through dust that blocks visible light, revealing structures in protoplanetary disks with unprecedented clarity. The images ALMA produces are stunning. Concentric rings and gaps, spiral arms and asymmetries, the signatures of planetary formation written in dust and gas. The disk around H.L. Tauri was one of ALMA's first major revelations. This young star, perhaps only 1 million years old, is surrounded by a disk carved with dark gaps and bright rings. The gaps almost certainly mark the locations of forming planets, their gravity sweeping clear the material along their orbits. We are seeing a planetary system in its infancy. The architecture of worlds being laid down around a star barely past its own birth. PDS 70 offers an even more direct view of planet formation. Within this young star's disk, 2 planets have been directly imaged, PDS 70b and PDS 70c. These worlds appear as points of infrared light embedded in the disk, glowing with the heat of their ongoing formation. They are still accreting material, still growing, still incomplete. Watching them is watching planets being born, a process that usually takes millions of years, compressed into observations we can make tonight. The gaps in protoplanetary disks are not always carved by planets. Some may arise from the physics of the disk itself, variations in temperature, magnetic fields, or the properties of dust grains can create ring-like structures. Distinguishing planet-carved gaps from other features requires careful analysis, but the accumulating evidence suggests that many disks do contain forming planets, even when those planets are too small or too faint to be directly imaged. Infrared observations reveal the thermal glow of young planets. A planet still gathering mass releases enormous amounts of energy. Gravitational potential energy converted to heat as material falls onto the surface. This heat makes young planets far brighter in infrared light than mature planets of the same mass. By observing at infrared wavelengths, telescopes can spot worlds that would be invisible at optical wavelengths, hidden in the glare of their parent stars. Spectroscopy adds another dimension to our observations. By spreading light into its component wavelengths, astronomers can identify the chemical fingerprints of molecules in disks and planetary atmospheres. Water, carbon monoxide, carbon dioxide, methane. Each leaves a distinctive signature. These observations reveal not just where material is located, but what it is made of, tracing the distribution of the ingredients that will eventually become parts of planets. The variety of protoplanetary disks matches the variety of mature planetary systems. Some disks are smooth and featureless. Others are carved with intricate structure. Some are massive and long-lived. Others are wispy and quickly dispersing. Each disk will produce a different planetary system, and studying many disks helps us understand the full range of outcomes that planet formation can produce. Comparing observations to theoretical models allows us to test our understanding of planet formation. When a model predicts that a certain type of disk should produce a certain type of planetary system, we can look for that type of system among the exoplanets we have discovered. The agreement is often good, but surprises remain. Hot Jupiters, super-Earths, and other unexpected planet types have forced revisions to our theories. Observation and theory refine each other in an ongoing dialogue. Future telescopes will reveal even more. The extremely large telescope, now under construction in Chile, will have a mirror nearly 40 meters across, large enough to directly image Earth-sized planets around the nearest stars. Space telescopes planned for the coming decades will search for biosignatures in exoplanet atmospheres. Each new instrument will peel back another layer of mystery, bringing us closer to understanding how planets form and whether any of them harbor life. Every disk we observe is a window into our own past. The processes shaping those distant structures are the same processes that shaped the disk from which Earth was born. When we see a gap being carved in a young disk, we see what Jupiter once did to our own protoplanetary disk. When we detect water ice in a distant disk, we see the raw material of oceans not yet formed. We are watching the universe repeat the experiment that produced us, learning our own history by studying others. The formation of a planet is only the beginning of its story. What happens next, whether a world becomes a frozen wasteland, a scorched desert, or a blue marble teeming with life, depends on a complex interplay of factors. Habitability is not guaranteed by existence. Most planets are hostile to life as we know it. Understanding what makes a world habitable helps us appreciate how remarkable our own planet truly is. The habitable zone is the most familiar concept in discussions of planetary habitability. This is the region around a star where temperatures allow liquid water to exist on a planet's surface. Not so close that water boils away, not so far that it freezes solid. For our Sun, the habitable zone extends roughly from the orbit of Venus to the orbit of Mars. Earth sits comfortably within this band, warmed to temperatures that allow oceans to persist for billions of years. But the habitable zone is only a starting point. A planet in the habitable zone is not automatically habitable. Many other factors determine whether a world can support life. Size matters. A planet must be massive enough to hold onto an atmosphere against the erosive effects of stellar radiation and its own internal heat. Mars, at the outer edge of our Sun's habitable zone, is too small to have retained a thick atmosphere. Its surface pressure is less than 1% of Earth's. Atmosphere composition shapes surface conditions profoundly. Venus lies at the inner edge of the habitable zone, receiving about twice as much solar energy as Earth. But Venus's thick carbon dioxide atmosphere traps heat so efficiently that surface temperatures exceed 450 degrees Celsius, hot enough to melt lead. A runaway greenhouse effect transformed what might have been a temperate world into an inferno. Atmosphere is not just a passive layer, but an active determinant of habitability. Magnetic fields protect atmospheres from being stripped away by stellar winds. Earth's magnetic field, generated by convection currents in the liquid outer core, deflects the stream of charged particles flowing outward from the Sun. Without this shield, the solar wind would gradually erode the atmosphere, molecule by molecule. Mars once had a magnetic field, but lost it billions of years ago. The subsequent loss of its atmosphere may have transformed Mars from a potentially habitable world into the cold desert it is today. Plate tectonics may be essential for long-term habitability. On Earth, the carbon cycle, which regulates atmospheric carbon dioxide over millions of years, depends on the subduction of oceanic crust and the volcanic release of gases at mid-ocean ridges. This cycle acts as a planetary thermostat, preventing runaway warming or cooling. Planets without plate tectonics may lack this stabilizing mechanism, leaving them vulnerable to climate extremes that could render them uninhabitable. Orbital stability affects climate over long timescales. A planet with a highly elliptical orbit experiences extreme variations in temperature as it swings closer to and farther from its star. A planet with a chaotic axial tilt might experience wild swings in seasons, with polar regions sometimes receiving more sunlight than the equator. Earth's relatively circular orbit and stable axial tilt, stabilized by the Moon's gravitational influence, contribute to the moderate, consistent climate that life has enjoyed for billions of years. The host star matters as much as the planet. Stars come in different sizes, temperatures, and activity levels. Red dwarf stars, the most common type in the galaxy, are small and cool, with habitable zones very close to the star. Planets in these zones are tidally locked, always showing the same face to their star, with one hemisphere in eternal day and the other in eternal night. Whether such worlds can be habitable remains an open question. Red dwarfs are also prone to violent flares, sudden releases of energy that can strip atmospheres and sterilize surfaces. A planet orbiting a calm, stable star like our Sun may have a better chance of developing and retaining life than a planet orbiting a temperamental red dwarf. The stellar environment is part of the habitability equation, a factor that lies beyond the planet itself. Moons can contribute to habitability. Earth's moon stabilizes our planet's axial tilt, preventing the chaotic wobbling that might otherwise produce extreme climate variations. The moon also drives tides, which may have played a role in the origin of life by creating coastal environments where chemicals could concentrate and react. A large moon is not strictly necessary for habitability, but it may be a helpful companion for any world aspiring to host life. The timing of planetary formation within a stellar system's history also matters. A planet must form early enough to accumulate the necessary volatiles, water, carbon compounds, nitrogen, before they are lost to space or consumed by the star. But it must also survive the period of heavy bombardment that follows formation. A planet that forms too late may miss the volatile delivery. A planet that forms too early may be pummeled into sterility before life can take hold. Water is central to habitability as we understand it. Every living thing on Earth depends on water, its unique properties, its ability to dissolve a wide range of substances, its behavior as it freezes and melts, its capacity to moderate temperature, make it an ideal medium for the chemistry of life. Whether life could arise in other solvents, ammonia, methane, exotic liquids, remains speculative. For now, the search for habitable worlds is largely a search for worlds with liquid water. The concept of habitability continues to evolve as we learn more. Subsurface oceans on moons like Europa and Enceladus suggest that liquid water can exist far outside traditional habitable zones, warmed by tidal heating rather than stellar radiation. Rogue planets with internal heat sources might harbor pockets of habitability in the darkness between stars. Life is resilient and adaptable. The boundaries of habitability may be wider than we once imagined. Earth is the only world we know that is unambiguously habitable, the only planet where life has been confirmed, the only world where we can walk under an open sky and breathe freely. Understanding what makes Earth special helps us appreciate both its uniqueness and its connection to the broader cosmos. We are not separate from the universe, but products of it, inhabitants of a world shaped by the same processes that shaped all other worlds. We have traveled far tonight, from drifting grains of dust to the blue curve of Earth seen from space, from the collapse of molecular clouds to the diversity of worlds orbiting distant stars. The story of planetary formation is the story of how matter organizes itself, how gravity gathers and shapes, how time and chance conspire to create worlds. And woven through that story is our own story, the tale of how we came to be. You are made of planetary material. The calcium in your bones was forged in ancient stars and incorporated into the dust that built Earth. The iron in your blood condensed in the protoplanetary disk sank to form Earth's core. and was later returned to the surface through volcanic processes. The water in your body may have arrived on comets or asteroids, traveling from the outer solar system to the inner world where it could participate in the chemistry of life. You are not merely standing on a planet. You are part of it. The atoms that compose your body are ancient beyond measure. Hydrogen, the most abundant element in the universe, has existed since the first moments after the Big Bang. Carbon, oxygen, nitrogen, the elements of life, were manufactured in the cores of stars that burned and died before our sun was born. You are assembled from materials that have been cycling through the cosmos for billions of years, temporarily gathered into the form you now inhabit. When you look at the night sky, you're looking at the forges where your atoms were made. Every visible star is a site of ongoing nucleosynthesis, fusing lighter elements into heavier ones. Some of those stars will eventually explode, scattering their enriched material into space, providing raw materials for future generations of planets and the life they might support. The universe is continuously creating the ingredients for worlds and for beings like us. Earth is a small world in a vast cosmos, but it is not insignificant. Here, matter became conscious of itself. Here, atoms assembled into molecules, molecules into cells, cells into organisms capable of wondering where they came from. The story of planetary formation is remarkable in itself, but it becomes even more remarkable when it produces beings who can tell the story. We are the universe contemplating its own existence. The processes that formed Earth are occurring right now around other stars. Somewhere in the galaxy, dust is gathering into pebbles. Somewhere, planetesimals are colliding and merging. Somewhere, a rocky world is cooling after a giant impact, its surface solidifying into the first crust. The universe is constantly making planets, constantly experimenting with the conditions that might give rise to life. We may not be alone. Whether or not other life exists, we are connected to the cosmos in ways both physical and profound. The same gravity that collapsed molecular clouds holds you to Earth's surface. The same nuclear physics that powers stars powers the sun that warms your skin. The same chemistry that built planets built your body. You are not a visitor to the universe, but a native expression of it, a pattern that matter can form when given time and the right conditions. Tonight, as you rest, the processes of planetary formation continue throughout the galaxy. Stars are being born in distant nebulae, surrounded by disks of swirling dust. Planets are growing, migrating, settling into orbits that may last for billions of years. Moons are forming from collisions and captures. Rogue planets are drifting through the darkness, carrying their secrets with them. The story we have explored is not just past history, but ongoing reality, a continuous creation that has no end in sight. You are part of this story. Your existence is possible only because of the specific sequence of events that formed the sun, shaped the planets, delivered water to Earth, and allowed life to emerge and evolve. You are the temporary custodian of atoms that have been on a journey lasting billions of years and will continue that journey long after you return them to the world. In a very real sense, you are the universe experiencing itself, a way for the cosmos to know that it exists. And so we come to the end of our journey tonight. From the faint wisps of interstellar dust to the intricate processes that build worlds, from the chaos of planetary formation to the calm of a mature solar system where life could take hold. We have traced the path from nothing to everything, from scattered atoms to the ordered complexity of planets and moons, and the beings who wonder about them. The world beneath you was once a cloud of dust. The air you breathe was once locked in stone, released by volcanoes over billions of years. The water in the oceans fell from the sky, and before that, it rode on comets and asteroids, and before that, it formed as ice on tiny grains drifting in the cold outer reaches of a protoplanetary disk. Everything around you is ancient. Everything around you is connected to everything else. If you are still awake, you can let these thoughts accompany you into sleep. The universe is vast, and you are small, but you are not separate from it. You belong here. You are made of the same materials as stars and planets, shaped by the same forces, participating in the same grand story. There is comfort in that connection, a sense of belonging that extends beyond the boundaries of Earth, beyond the boundaries of the solar system, to the farthest reaches of the observable universe. Let your breath slow now. Let your body settle into rest. The planets continue their orbits, indifferent to our waking and sleeping, our worries and joys. The stars burn steadily, converting hydrogen to helium, building the elements that future worlds will use. The dust drifts, patient and quiet, waiting for gravity to call it into something new. And you rest, a small, warm presence in the darkness, made of stardust and planetary material, dreaming the dreams that matter can dream when it has learned to think. If you happen to still be awake, you can go ahead and watch the next video now. But if your eyes are heavy and your thoughts are soft, simply let yourself drift. The story will still be here tomorrow. The universe will still be making planets, still gathering dust into worlds, still spinning out the conditions for life and wonder. You are part of that story, and you have all the time you need. Sleep well, dream of distant worlds and ancient light, and know that wherever you are home. Good night.